Well, I hope you're doing okay after a long night. I hope that everyone's happy today and everyone's ready to get started on a powerful topic. Da-dun-ts. All right. So this topic is about power. This is actually a little bit different than most of our statics topics that we have dealt with because time is now going to be a factor. Basically, we haven't really used time as a factor in anything that we've done up till now in this course because, it's a statics course. So we typically kind of think of things that are just sitting there, not moving, but now we're going to have to look and see, we'll deal with time just a little bit. To help us out and still make us feel like it is a statics course, though, we're going to look at situations where, even though time is a factor, we're really not going to look at like the status of things changing over time. And we'll see what that means here in just a few minutes. So what I'd like to start with here is I'd like to start with coming up with a way of describing how much energy or power is associated with sort of forcing a shaft to turn, right? We've looked at torques in here, torques applied to shafts and such. And whenever you have a torque applied to a shaft and then that shaft is allowed to rotate, that rotation of the shaft actually involves a transmission of energy or power, right? If there's both a torque as well as a simultaneous, angular movement, that means that there's going to be some energy that is either delivered to or taken away from the shaft. And so we're going to look at some of that today. And so to get started with that, I want us to think about a fairly simple case here, but this case has basically a weight that is hanging from a rope, and this rope is being wound around a spool of sorts here. And the reason that it's about to be wound around this spool is that we are applying a torque of T to the end of this shaft right here. Okay? So one way we can look at this is that we're applying a torque of T to one end of the shaft, and there's going to be another torque that is reacting against it on the other end of the shaft. That other torque is probably coming from the fact that there's this weight that's hanging off of here. So let me start by just telling us or giving us a value for what this weight is. Okay? Let's say that this is a force of F, just to make the variables easy. Okay? So that, we can think of it as a weight, but whatever the force is that's pulling down on that thing, let's call it F. Okay? And the first thing I want to ask is, because of that F that's pulling on that, that string that's attached up to that pulley, what is the torque that kind of action of that force pulling on the string, which then goes around the spool, what torque does that imply? Based on what we've kind of labeled on this figure so far. Okay? Well, it would kind of be, I'd actually kind of be pulling it counterclockwise the direction we're looking at it, but I'm trying to drive at something a little bit different. What would the value be of the torque if we know F and we also know the size of the pulley, and specifically R? All right? What is that torque? Okay? So torque is going to be F times R. And if we go ahead and then further specify that this system, maybe it's rotating, like maybe it does have some kind of angular speed to it, but let's say that it's not angularly accelerating, right? Nothing's changing speed, as it sits here doing this. If that's the case, then we can say that F times R is going to be equal to that torque that we're applying over here. So the essential balance that we're looking at is that there's a tendency to want to rotate this thing counterclockwise because this F is acting at a distance of R, but then there's another tendency to try to make it rotate clockwise because we have T, and if we know it's not accelerating, then F times R has got to be equal to T. With me so far? Okay, that's all we're doing there, by the way, is just an equilibrium equation. I didn't do it very formally, but that's the reasoning that we use to get to that point, is that if this has to be an equilibrium, then F times R has got to be equal to T. Okay? Well, let's say that we still pretend like it's an equilibrium, but now let's say that it has moved. Maybe we think of it moving very slowly at a constant speed or something, but let's say that it moves from its current position, right? And I'll describe that current position with sort of a line that goes back to the center right here. And let's say that as a result of kind of twisting on this shaft, that point of attachment right there basically moves to a new location, right? So that this thing has basically kind of shifted through an angular displacement there of a certain angle, all right? And let me give that angle a value theta, okay? When it does that, does it lift the weight, assuming that the rope doesn't stretch or any funny thing like that? Okay? So what we could see there is that this little weight right here is going to be lifted. Okay? So let me kind of put that on here like this just to make the picture look very, very clear, right? It has now lifted a little bit because that thing has pulled on it. And, you know, I'll even change the color a little bit there. So is there a relationship, is what I'm going to ask here. Is there a relationship between the theta that we had up here and the amount of distance, I'll call it d, that this piece moved as a result of twisting that, that spool through that angle?
D is going to be the arc length.
Okay, he says that d should be the arc length that is swept because we have this theta acting on this spool right here. We have this theta, you know, that has basically caused the outer perimeter of the spool to move around and wind up a little bit more of this rope. Okay? Now, I did put this little blue line over here on purpose because I'm going to collect a few things that have to do with units over there on the right side of the screen. Okay? So I'm going to maybe put over here notes about units. Okay? And the reason that this matters is that the very first thing that we need to think about is what do we mean when we measure something in radians? So I'm going to put here radian measure. What is it we're doing when we do a radian or a number of radians? Okay? Well, here's what we mean by that. We're talking about an arc length per radius. Right? So this might be kind of handy because in our case, we've got an angle, and there's no problem with us thinking about trying to measure that angle in radians, right? This little angle of theta that we put right here. We can think of that angle in radians. And what this tells us is that if we know that number of radians and the radius, we should be able to find arc length, right? And what did we just say the arc length was of the amount of rope that got wound up on this spool? D, right? So this basically gives us another relationship that we can apply right here that basically goes from, you know, from angle to distance. Okay? So what would that look like? D should be equal to what? Theta measured in radians, right? Times what? The radius. Because basically I'm taking this definition of radian measure, rearranging it a little bit and saying that arc length, which we're going to say is d, is going to be equal to the radian measure theta times the radius that's associated with that twist. Okay? And by the way, up here, this was torque. This is kind of how we relate torque and force. Right? We've got that relationship right there, and then we've got another relationship that gives us a relationship between angle and distance, okay, and with radius also in there. All right, now let's think about another one. You guys are familiar with the idea of work, right? You say, I've been taking this class almost an entire quarter. I'm certainly familiar with the idea of work, right? So, work, how do we define it? Which, by the way, work is another word for like mechanical energy, right? How do we define it though? Okay, force times distance. Now, that's actually easy enough for us to look at with respect to the force and the distance that I had for the little weight that was being pulled over here, right? So we can think about the amount of work that is associated with moving this block, right? And it's just going to be equal to F times D. right? Okay, well, is there anything else that I can do with that F times D? So actually, let me shift this over and say work is equal to F times D, right? Okay. Is there any kind of substitution I can do with F times D? Like, can I substitute anything in for D? Yeah, theta R, right? So that would be D. What about F? Yeah, you could rearrange this and basically say that F is equal to T over R, right? Okay. Yeah, we got T over R here. We got that times theta times R. And so then what he says is that that means that these R's, because it's the same value, those R's cancel, and you just end up with torque times theta. Okay? So this is actually a nice little relationship that we already have here, is that when we're trying to look at how much energy is being put into a shaft, all you have to do is take the torque that's applied to the shaft, multiply by the angle through which the shaft rotates. That's an amount of energy that has been put into the shaft. But do be careful. It's very important that that theta be measured in radians. Why? Because that was integral to our little discussion here, right? That was integral to like how we justified making that move of having D is equal to theta times R. Theta had to be measured in radians for that to work, right? So make sure that you're measuring that theta in radians. Okay? Well, now, what is, if I was going to shift to the next little line here, let me say we're going to deal with power next. What's the difference between energy and power? Rate of energy flow. That's a great answer, right? Power is a rate of energy flow. And one of the ways that you can get that is you can kind of just think about dividing work by time, like work per time, right? How much energy per time was associated with this. So literally what you can do if you're trying to turn this into power is you can kind of go through and think about dividing each of these by time, right? Kind of divide through the whole thing by time. And when you do that, what you end up with is on the left side, that's going to be power. Okay? Now, for the F times D, is there any kind of way that we can maybe consolidate some variables there with F times D over T? Yeah, this D over T, someone observes out here, that's just the velocity of that block, right? How much did it move divided by, how much time did it take to move, right? So what that tells us then is that this is just going to be kind of like force times velocity. Okay? But we're still not done because we have even another expression of it over here. Is there anything we can do with theta and t in that expression over there? Yeah, so this is just angular velocity, right? Okay, and actually let me do it the same order here. Torque times angular velocity. Okay, and so kind of our big thing that is sort of the new equation that I'm going to show you today, we have actually already had one where it was work is equal to t times theta, but even bigger than that is this one here, and it's that power is equal to t times, we give this a fancy letter omega, angular velocity. Okay, so there's kind of our big equation that we get to use today that might be kind of new. We haven't necessarily covered in another class before. Okay, now I want to go back and kind of think through some of these units again. Okay, because we've got some interesting things that sometimes overlap. Like for instance, when we have torque, right? We know what the units are for force and for radius, right? Force would be in something that would be like pounds or newtons. Radius would be in something that might be like, meters or feet or inches or something like that. So we basically know that it's force times length for torque, right? So let's say something like Newton meters or, foot pounds, that kind of thing. What about energy, though? Oh. Okay. Now, if you look at this, right, when you talk about energy, we still have a force times a length, right? So would it be valid for us to say, well, you just use Newton meters again? Okay, maybe a tricky question. Yeah, it's valid. But usually what we do if we're talking about energy, instead of, in the SI system at least, when we're talking about energy, instead of writing it as Newton meters, we usually write it as joules instead. So this is kind of interesting because if you're using a program like MathCAD very often will take Newton meters and just assume that you want it to put joules on the screen, right? And sometimes you might, and it's not invalid, it's just kind of customary that if you're talking about torques, you usually go ahead and separate the newtons from the meters, whereas if you're talking about energy, you often collapse those down into something like joules, okay? Now, in the US system, do we have something that's sort of like the unit of joules? It depends on your context, okay? We kind of do, but we don't have it quite as clean as joules. The closest we've got that I know of, at least in kind of in the U.S. system, is you can talk about BTUs. BTU is a unit of energy, right? But we don't usually use it in these contexts. What do we do instead? We just leave it as foot-pounds. That's kind of the customary thing to do generally in the US system, is just not collapse it down into something that's just a unit of energy of some kind. Okay? All right, well, what about power? All right? Do the SI system first, right? So in the SI system, what's a unit that you know of for power? Okay, most of you are familiar with the unit of watt, but what is a watt? Okay, which you use the letter W here. Someone says it's a joule per second, which is just a Newton meter per second, right? Well, that's really handy. We've got all those that are nice and clean. Let's look at the US system. Do we have a unit for power in the US system? Actually, we do. Horsepower. Okay. Now, what's a horsepower? Okay. Now, someone says, like, what's the energy output of a horse, kind of, right? Like, and that actually is the roots of what a horsepower is. It's about how much energy sort of a standard horse might be able to sustain over a period of time, right? How much power output that they could put out. But that's not really how we use it anymore, but we still use the unit, right? But do you know what the unit is relative to other things that we might know? Okay, you're not too far off. He says that a horsepower, I'm going to put that down here, a horsepower is approximately 700, and I think he was off maybe just a little bit. He said 747 or something like that. It's actually 745.7 watts. Okay, so that's not necessarily always the one that I go to first, but this is actually a very handy little conversion to know how to go from horsepower to watts or back and forth. Okay, but horsepower actually does have a definition in terms of U.S. units as well, and I'll have to probably tell you what it is because it's probably unlikely at this time that you may have seen this before. It is 550 foot-pounds per second. Okay? And if you think about, you could also express that in inch-pounds per second, right? It would be more inch-pounds per second than foot-pounds per second. So you'd basically multiply that by 12. Another definition of horsepower is 6,600 inch-pounds per second. Okay? So these are some handy units to know about. As a matter of fact, I was given a test last night to some of my seniors, and I had a student get very distraught because he could not remember what the conversion was to go from foot-pounds per second to horsepower. So, you know, I had compassion, just in case anyone was wondering. So, all right, so these are some units that we want to keep in mind, and why don't we go and kind of look at this next little thing I want to look at, and that is this idea that when we're talking about transmitting energy or power, I put energy here, but this is actually just as applicable to power as energy. It kind of matters what direction the torque is being applied and what direction the rotation is happening. Because in one case, you are supplying energy into the shaft, and in the other case, you're actually removing energy from the shaft. And I thought a really good kind of practical way that I could show this is with a PTO shaft that comes out of a tractor. Some of you have some experience with this, others of you might not, but basically a PTO shaft on a tractor is designed to deliver energy to some implement that you put on the tractor, and it does that just by rotating that shaft, right? So the source of energy is the engine of the tractor. It's then, you know, putting that energy through the PTO shaft and going to the thing that needs the energy. So if I was going to kind of label some things here, you know, I would basically say this is, to use a fancy word here, this is an energy sink. This, it's like a lawnmower kind of thing. Some people call it a bush hog, right? So this energy sink over here is what needs the energy. What's the energy source? Okay, it's going to be this tractor over here. Okay, and let's say that this tractor begins to supply energy to the energy sink there, and in doing so, it starts to rotate this shaft in this direction. Okay, what direction do you think, so I'll put an omega on there, kind of indicate that's the angular speed in that direction for that shaft. Which direction do you think the tractor is like putting torque on this shaft that goes from the tractor to the, you know, to that bush hog? Okay, I'll let you know. If you're delivering energy to the shaft, it means that the torque that you're putting on the shaft is the same direction as the speed of the shaft, like the direction that it's turning. Okay, so this is what I would maybe call T source. Okay, and that's the torque that's being applied to the shaft, not the other way around. I'm not looking at that as the source that the shaft is applying to the tractor. Okay, but what do you think happens on the energy sink side? Okay, if the shaft is not accelerating, then I better have the same torque, right, applied at the other end of this shaft, but in the opposite direction, right? And so I could maybe call that T sink. And these terms source and sink refer to what is supplying the energy and what is using the energy. Okay? So this is kind of just so that you know, whenever you have a situation where you have a torque that's being applied and it's being applied the same direction as the rotation is happening, that means you're delivering energy to the shaft, right? Whereas if you have a torque that's applied and it's the opposite direction of the direction it's rotating, that means that the shaft is delivering energy to the thing that it's attached to. Okay? With me so far? Okay, so that's what I wanted to get across there with the idea of energy sources and energy sinks and the direction that you can expect that the torques are going to be applied. The other thing that we want to touch on today is the idea of transmitting torque through gears. And some of you might remember a freshman level treatment that we did of this. We're going to change this up just a little bit from the freshman year, although it will kind of still tend to work the same way. I want to do it now in terms of thinking of angular movements of these things as being measured in radians as opposed to being measured in revolutions, because it's a little bit cleaner of a derivation if we do it that way, but we'll get to that in due course here. Let's start by looking at this system right here that has an R1 and an R2. And let's say that we're applying a torque, kind of delivering a torque into R1, and I will call that T1. Okay? And just because I want to sort of, notice with the signs that we get out of this derivation, whether or not there's a reversal, let me just assume to start off with that I'm going the same direction with a torque on the second one. That way, if I end up calculating it and coming up with something that's the same sign, like if it's a positive sign, what does that mean? It means that means that I chose right? It means that my assumption was correct, right? What if I end up getting a negative sign? It means that, they probably go opposite each other instead of the same as each other. Okay? So let me put in T1 and T2 like this, and then let me do free body diagrams of the two gears. Okay, so let me do the top one up here first, and then I'll do the bottom one down here. Okay? They have a little shaft that they rotate around. Are there reactions that happen at that shaft? Okay, you might guess, based on the fact that I'm drawing some, that there are going to be some reactions there. That's what holds it spatially in the right place. Those aren't actually the focus of what I want to look at, but it's probably still important to draw them on there. And then we also have T1 acting on this one as a torque being applied to that shaft that goes to the middle of that gear. And then I've got this T2 that I assumed was being applied to this one. Okay? All right. What is it that keeps the upper left gear from accelerating? Like right now, wouldn't it accelerate angularly clockwise around the center if I didn't do something else with that upper gear? There's something resisting the idea that it would try to move clockwise. And what it is that resists it is the fact that it has an interface force right at the point of contact between these two gears right here. There's a force that acts between those two things. And I'll actually spare you a little bit and let you know that the real nature of the force between real gears has both a normal component that would try to push the two gears apart, as well as a tangential component that actually does the transmission of torque. And for now, I'm going to let you ignore the idea that there's a normal component of force acting right here, because it's not that important to us with what we're trying to accomplish with this talk, okay? But I'll just make mention of the fact that unless we sort of decide to ignore it, there would be forces that would push these two things apart from each other, okay? But we are going to ignore that and instead look at only the effect that does the transmission of torque, right? And that would be what direction for the upper gear? Okay, if it's not accelerating clockwise, then it means that there must be something keeping it from accelerating clockwise, right? So let me call that just a force of F. Okay? Now, Newton's third law says that if there's a force of F acting that direction on the upper left body, what must be acting on the lower right body? Something that's equal in magnitude, opposite in direction, right? So that'll be F acting right there. Okay? Also, we remember that we had R1 and R2 on the original figure as the sizes of these gears. Let me actually show those in a strategic location. Let's say that that is R1 right there, and this is R2. Can we use the relationships that we have on these two figures to come up with a relationship between T1 and T2? Okay. Yeah, so basically, someone started to state the relationship there. What you're doing, though, is you are taking a sum of moments around the shaft, right? The pin or shaft or whatever you say is right there. And you're saying that we've got a counterclockwise moment of F times R1 and a clockwise moment of T1, and that has to be equal to 0. With this body here, could you do the same thing? Okay, summation of moments around the shaft of that second piece. And for that one, we would have, okay, a counterclockwise of FR2 and a clockwise of T2, and that would be equal to 0. Between these two equations, are there any common factors? Okay, F is a common factor between these two things. So we could actually solve these out for the F's, right? So with this one, what does F become? It looks actually just like our initial discussion we had of that pulley up there, right? F is just going to be equal to T1 over R1, right? Okay, and then what? Can we do that same thing here? Okay, F there is also going to be equal to T2 over R2. But F is the same for these two things, and so we basically say that T1 over R1 is equal to T2 over R2. All right? Or another way that you could do this by just sort of rearranging the equation a little bit, you could also say that T1 over T2 is equal to what? R1 over R2. And now I'm going to, maybe make you wonder about this a little bit, but could this also apply to diameters? Could you multiply numerator denominator by 2? That would turn it into diameters, right? And that's mathematically acceptable. So we could say this is actually equal to D1 over D2, where D1 and D2 are diameters. Okay? Now, let me ask you this. Do diameters relate in some way to circumference? How does that work? Yeah, I could multiply numerator and denominator each by pi, and then what I would have is like the circumference of 1 over the circumference of 2. Okay? Now we're going to go even another step. I've shown these gears right here as being like smooth rollers, but they are only shown that way just to kind of give you the basic idea of how they interface with each other. And with real gears, they do actually have these things called pitch circles, and they behave as if the two gears are like rolling with friction on those pitch circles. So that's not a fake thing. They actually really do behave that way. And what we're looking at here are like the pitch circles that would actually interface with each other. But real gears have teeth that actually mesh to the inside and outside of the pitch circle. Do you agree with that? Well, once you say it has teeth, is it possible to, say, mesh one of the gears in the transmission of your car with a gear that comes out of your watch? Why not? Those teeth, yeah, those teeth have a certain size to them, right? That size is sometimes known as being a pitch, right? And the way pitch works is it's a number of teeth per unit of diameter or per unit of circumference, right? And in order for gears to actually mate with each other, they have to have the same number of teeth per unit of circumference, let's say, or else they won't mate with each other. Okay? So what else can we do with this maybe? If pitch is number of teeth per unit of circumference, what if I multiplied numerator and denominator by pitch? Yeah, so this actually turns into the number of teeth on gear 1 versus the number of teeth on gear 2. Okay, so all these relationships hold whenever we're talking about the kind of the gear ratio between two gears. Okay, and I guess I'll put a box around that. I'm going to also put a little asterisk right here because we're going to change this up maybe just a little bit in a few minutes. This is assuming zero loss. Okay, discuss that just a little bit more here in just a few minutes. But right now we're assuming there's no loss happening anywhere. Okay, what about speed? Okay, let me do the same thing I did with torque and say, let's just say that this upper gear is rotating with an angular speed of omega 1. And just like I did with torque, let's start off by assuming that they go the same direction, right? Both of them are going clockwise, omega 1, omega 2 here. Okay? All right. So now let's look at the upper gear. Kind of isolate that upper gear just a little bit and say we've got it spinning at omega 1 this direction. Could I, at the location of interface between these two gears, figure out what the instantaneous linear velocity would be of that point of interface? I could draw that on here like this. Say, right at this instant in time, there's a speed that that little point of interface between these two bodies has. Okay, we're getting close. He says, is omega equal v squared over r? Okay. It does have to do with r. This is, let's remember, that's r1 right there. Okay. But let's actually remember what our definition was of radians. What is a radian? Radian measure, maybe I'll say, is arc length per radius. Okay? What if I take this and I say, what's the rate of radian measure? Like, how fast are your radians changing? You divide that by time. And let's say you divide this by time. Okay? Now, when we look at this, what is arc length per time? Like, what if I was to take this radians out and multiply it by the left side? Like, multiply this by radians. Radius, I should say. Okay? That leaves me with arc length per time. What we do is we get right back to what we did up here a second ago, where we related our, kind of our speed by having theta over t, and we had d over t here as well. It's basically the same type of thing that we're doing down here, but it relies on that definition of radians. So I'm going to say that this velocity right here is going to be equal to omega 1 r1, because it's basically the radian measure per time. That's your angular velocity, right, omega 1, multiplied by radius. That's going to be equal to my arc length per time, which is like linear speed. With me? I know that got a little bit messy right there, but that's basically what we're doing and why it is that that v is equal to omega 1 r1. Okay? Can we do the same thing on the other gear? Okay? The v that I have here is going to be what? Yeah, because it's going to be based on this omega that I assumed it was this way. Okay, omega 2. And we still have r2. But there is a problem here. What is it? The first one made total sense, right? Omega is going clockwise. That looks like the same direction I drew my velocity right there. What about this one? Omega 2 is going clockwise, but I drew my velocity this way. Yeah, so in order to make this work, I've got to say, well, this had better be equal to minus omega 2 r2. Okay, and so out of this relationship, since this v is the same in these two cases, what we can do here is we can say omega 1 r1 is equal to minus omega 2 r2. And what does the minus mean? Really, the only reason I write it this way is to remind you that anytime there's going to be a mesh of two gears, there's going to be a change of direction. right? So you have this gear meshing, the upper gear meshing with the lower gear. The upper one's going to go a different direction than the lower one. And if you just do it out by assuming they go the same direction, and then you see that you have to have a negative sign in there to make that work from the standpoint of the math, that can remind you that they go in opposite direction. That's the only reason I leave that negative sign in there, is to remind you that when gears mesh, they actually turn opposite directions. Okay? Well, what can I do with that? Okay? Yeah, we can basically say that omega 1, let me do it this way, omega 1 over minus omega 2. That way I can get rid of that minus sign out of the main part of it, right? Just it acknowledges they go two different directions, but we'll just put it down there like that. Omega 1 over minus omega 2, what is this going to be equal to? All right. It's going to be equal to R2 over R1. And by the way, all the other relationships that I laid out a second ago still hold too. D2 over D1, C2 over C1, where those are circumferences, or N1 or N2 over N1 for numbers of teeth. All right. So over here we had our relationships for speed, and then over here we have our relationships for torque. But let's go back and try to remember what we had for power. What was our equation for power? Torque times omega, right? So if I go down here, and what if I combine these relationships? Right? What if I take T1 over T2 and multiply it by omega 1 over omega 2? Right? Or I could leave the minus sign in there if I wanted to, right? T1 over T2 times omega 1 over omega 2. Okay, minus omega 2. I could put the minus in there if I want. What is that going to be, though? Okay? Yeah, if we actually plug these in, it's going to be equal to N1 over N2 times N2 over N1. Right? So everything cancels. And what does this tell us? Okay? It tells us that if we assume T1 and T2 are in the same direction, and omega 1 and omega 2 are in the same direction, right, then the ratio of these two things together, right, I would say, P1 over minus P2, that's basically what we have there, right, is going to be equal to 1. Or we can just say P1 over P2 is equal to minus 1. Okay, now the minus gets confusing for people, and so let me kind of explain it once, and then I'll probably ignore it from here on out, the minus, okay? So the minus is confusing because we assumed both of those torques were delivering energy into the system, right? If we assume that both torques are clockwise and both of the omegas are clockwise, then both of those are delivering energy into the system. But is that possible? Is there any place for the energy to go? No, like there's no sink for it. So the way it works instead is that one of those directions actually switches, but the torque direction stays the same, right? The direction of rotation switches, but the torque direction stays the same. And so let's say that it's omega 2 that's wrong, right? It's actually not going that way, it's going the other way, right? In that case, then this would be the source up here. And this would be the sink down here, because down here you have your, if this was actually not going the direction I said and instead it was going that way, right? Then that means your torque direction is opposite the direction of the actual rotation, so you're sinking energy in that one, whereas you are providing energy to the top one. Okay, so that's where that minus sign comes from, is the idea of one of them's got a source and one of them's got a sink. But for a lot of what we do, we kind of just pretend like we've dealt with that in another way, and we don't even look at that -1 anymore, right? We sometimes will write an equation a little bit differently so that we say, this is a power that comes into the system, whereas this is a power that goes out of the system. And then we just deal with it by, by doing that. Okay. Let's move on a little bit here and answer this question. Do gears really transmit energy with no loss? Right? It seems to imply that where we look at this ratio up here of the power in, right, P1 over power out, P2, and they're just equal to 1. Right? They're equal to each other, right? If the ratio is equal to 1, they're just equal to each other. Power in is equal to power out, right? Okay. Is that really what happens? Okay. In the real world, things work a little differently, right? And so I want to show you a little bit about how this actually works in this real world. So let's actually, I guess, though, still start with the lossless case. So in the lossless case, what we have is that P in minus P out is going to be equal to 0. Fair enough, right? We're saying however much we deliver in, that's the same amount that comes out. So then we say T1 omega 1, that's the amount coming in, minus T2 omega 2, that would be the amount going out. And everybody's happy, right? This is doing the same thing, by the way, in another little kind of different way. We can actually plug in what we had for T2. T2 is going to be equal to T1 times N2 over N1. Whoops. 2 over N1. Okay. Times omega 2, which omega 2 is just omega 1, times what? N1 over N2. Okay? And so we can basically see in another form why it is that, this is lossless, right? We're saying the amount of power in and the amount of power out are the same as each other. These N1s and N2s cancel out. We end up with T1 omega 1 minus T1 omega 1 is obviously 0. Right? Everybody's happy. Well, what about if we do this where we don't have it lossless, right? So I'm going to say, what if it's less than 100% efficient? Okay? That means that we have to define efficiency. Do you guys remember dealing with efficiency at any point prior in your curriculum? Okay? Probably. And you probably remember that efficiency is defined as what? Okay? Here's how we defined it a while back. Useful power or energy. I'm going to define it in terms of power. So useful power out divided by what? Required power in. Okay? What does that look like for our situation that we were doing up here? Okay, let's think about P in minus P out. Instead of saying it that way, what if we do it with, P out, which would be T2 omega 2 over T1 omega 1. And we're saying that is going to be equal to this efficiency, and there's a fancy symbol we give that, eta. Okay? So there's our efficiency equation. Let me ask you a question about that, though. With this omega 1 and omega 2, is there any way for the ratio between omega 1 and omega 2 to ever be different than, than it is whenever the gears mate with each other? Or maybe another way of asking it would be, what would that physically look like if those gears didn't have the ratio? So basically what we're saying here is that we're now saying that this is no longer just has to be equal to 100% or 1. We're saying this can be something else, meaning that the numerator and denominator are going to be different from each other, right? And so, one of the ways we can kind of think about that is, well, is there any kind of a way for, I'll tell you what, let me actually rewrite this a little bit. What if I rewrite omega 2 as omega 1, right? How did I rewrite it up here? Times N1 over N2. Okay. All right, and then I divide all of this by T1 omega 1. All right? So here's my question. Is there any kind of a way for there to not be this ratio between omega 1 and omega 2? Okay, and I'll answer that. I said, what would it look like physically? What this would look like physically is that the gear teeth would actually start to skip, right? That's the only way that you can have a different ratio between your one gear and the other than you predict by the number of teeth, is if the teeth actually start to skip one relative to another. If they don't skip, then you will not have a different ratio between omega 1 and omega 2 than is implied by the ratio of the number of teeth. Okay, does that make sense? So if that's the case, where is this ratio becoming something other than 1? All right, basically what we're saying here is it's valid for me to just say omega 2 is going to be that ratio of omega 1 times N1 over N2. That means I can divide out the omega 1, and where is this efficiency, or this inefficiency maybe I should say, happening? In the speed factors or in the torque factors? In the torque factors, right? That's kind of what I was driving at with all of that. So I can actually solve this out if I want to and say that, if you kind of think about this, if I multiply over here by T1, right, and say, well, actually, let me do it this way. T2 is equal to our efficiency times T1 times what? N2 over N1. And you'll notice there, that was what I had. It's mostly what I had for what I, plugged in for T2 in that expression up there. But now we've tacked on this efficiency value that is something less than 1, right? And so if you want to know how much torque gets transmitted into the torque sink, this is where the energy's going, right? You take your efficiency value, multiply it by your torque source, and then also include your gear ratio, N2 over N1. Does that make sense? How to include what this efficiency is going to be in the process of determining how the torque actually transmits through real gears. Okay? I'll bet if we do an example problem, it will make it even more clear. Would you like to do that? I have one vote for yes, and so I'm going to move on ahead. All right, so here's an example where I've got a motor that's driven with a voltage of 400 volts DC. It converts the electrical energy to mechanical energy at a 70% efficiency value, meaning, basically 70% of the electrical energy that is delivered to the motor gets turned into mechanical energy. Okay? It then drives through a 19-tooth gear up here at gear 1 into a 63-tooth gear on gear 2. That gear 2 is actually rigidly connected to gear 3. Gear 3 has 24 teeth. It mates with gear 4, which has 57 teeth, that drives this machine down here, and the machine requires 700 newton meters of torque and 250 RPM of speed. Right? That's how it's being driven down there at the end. Okay? What the example text says up here, it says, assume all the bearings are frictionless in the setup. Assume all gear meshes transmit power with 95% efficiency. Okay? And then it says, find the speed that the motor must turn. And then it gives us instructions here. This is so we have to deal with multiple kinds of units. We want to do that in both RPM and radians per second. Part B says, what's the torque transmitted in gear 2, 3, right? That's actually kind of one body. That's why it says, there's a particular torque that's transmitted in that body 2-3. And then it says the torque that the motor must supply. We're trying to find the torque that the motor has to supply to drive this machine like this. And then also the power that the motor must supply to gear 1 in order to drive this gear train like this. Okay? And then lastly, the current that has to be supplied to the motor in order to make all this happen. So these are all the things that we're going to try to find. Okay? Where shall we start? Part A. Okay. How do I determine how fast the motor has to spin? There's kind of two ways I can do it. I can either do it piece by piece, or I can do it all at once. Okay? Here's what I mean by that. One way I can do this is to determine how fast gear 2-3 is spinning. So let me denote that with omega 2-3. Okay? How do I determine what that would be? Okay, well, I can multiply it by, and let me explain how I do this. I very seldom go back and look at the equations that I derived just a few minutes ago for numbers of teeth and how fast things are turning. What do you think I remember instead? Smaller gear goes faster. Bigger gear has more torque. Smaller gear goes faster, angularly. Bigger gear has more torque. Okay? So when we go from the machine where we know the RPM of the machine and you want to go up to what's the RPM of gear 3, what direction should that ratio go? Right? 250 RPM times what ratio? Should make W or omega 2-3, it should make that go faster. Right? So what should the ratio be? Okay, 57 over 24. Okay, so I'll plug that in, right? 250 times 57 over 24. Now you might notice that I did put the minus sign in there. Okay, this gives me 593.75. Units? RPM. Okay. You might notice that I did put that minus sign in there. Okay. Why? Well, it turns out it is actually kind of a handy technique to use when you're trying to determine the directions that each of these pieces goes. Right? So whatever direction the machine had to be turned, the speed that the 2-3 member has to go is this speed, but opposite the direction that the machine was going. Right? What about when I go to my next step? Okay, omega motor. What I do there is I understand that the speed that my omega 2-3 is going there, right, which is minus 593.75 RPM, it goes even faster when it gets up to the motor because the motor has a smaller gear than that one, than the gear 2, right? And so I just multiply by that ratio, right? Multiply it by 63 over 19. Okay? But then what I actually do with this is, again, I apply another negative sign because I do that on all of these, right? The negative that I had here was because that was the value of omega 2-3, but I put another negative sign out there, and what does that indicate? It reverses again, right? So it started out the direction of the machine, it got reversed the first time to go opposite the direction of the machine. It reversed it again, this time to go the same direction as the machine, right? And you can kind of keep track of that with the signs like I'm showing you right here if you would like, okay? I tend not to. Whenever I do these problems, I usually look at it and I evaluate the direction that things are going just by intuitively looking through the thing and flipping the signs through, right? That's okay to do as long as you feel comfortable with it. Otherwise, you can try to use the math and like trace through and see how it flips direction each time, okay? All right, so this becomes 63 divided by 19, right? So that would be 1968.75 RPM. Okay, so that's one of the answers we needed to get. What's the other one that it asked us to do? Okay, it said do that in RPM, but also give it to us in what it is in radians per second. So what is that? Like, what's that conversion? Tell you what, one of the things that helps you with that is instead of writing that as RPM, sometimes it helps people to write it as revolutions per minute, because that's the same thing, right? RPM stands for revolutions per minute. So it's valid to put rev over min, right, to be like revolutions per minute. That sometimes helps you remember what kind of conversions you need to apply. To go to radians from revolutions, what do you got to do? Yeah, 1 revolution is 2 pi radians, right? So that means you're going to put 2 pi radians in a numerator and a revolution in the denominator. Okay? What else are you going to do? Because it says it wants it in radians per second, right? You have minutes, you want seconds. Yeah, so in a minute, there are 60 seconds. Okay? All right. So if we plug those in, I'll spare you the calculator punches, but if you punch those in, what that ends up giving you is 206.17 radians per second. Okay? And it's in the same direction as the machine. Okay? Done with part A. What should we do now? Part B. All right. So part B says we're supposed to find the torque transmitted in gear 2-3. All right. How do we get to that? Okay, yeah, we're still going to use some ratios here. Smaller gear turns faster, bigger gear, more torque. Right? Smaller gear faster, bigger gear, more torque. Okay? And so what we can do here is understand we're trying to get the torque in gear 3, right? Or maybe I'll put 2-3 because it's going to be the same torque in applied to 2 as 3 because they're just connected to each other there. All right? So torque 2-3 is going to be equal to what? 700 Newton meters times what? Bigger gear, more torque, smaller gear, faster. Actually, so that means smaller gear, less torque, right? So is there more torque in 3 or more torque in 4? Okay, so that means we better be multiplying this by 24 over 57, right? That'll make it be less torque going to that next piece, which that makes intuitive sense, right? But I'm missing something. These only transmit torque with 95% efficiency. Okay? Well, if we want, we can go back up and remind ourselves how to deal with that, right? We're looking here at there being a T2 as a sink with an efficiency times T1 being the source times N2 over N1. in this problem, which one is the sink and which one is the source?
The source is the machine, the sink is gear 2, 3, or the torque consumed.
Okay. So my question is actually this. Which way is energy flowing? Okay, I saw someone do this with their hand, right? It's coming from the motor to that gear, from this gear to the machine. So which one's the source? This is the ultimate source, right? It goes down through one of these gear sets and then down through the other set. So where do we apply our efficiency? Because it's very tempting for you to just say, oh, well, let me just multiply this by 0.95, right? Does that make you cringe right now? It should. That should not be on my page right now. Why not? Because this is the source, and this is the sink. And what direction were they in this case? The other way, right? And you've got to make sure you put that on there the right way, or else you're going to apply your efficiency the wrong direction. You have to be aware of what direction the energy is flowing in order to properly put your efficiency factors into these. Okay? So where do we put it instead? I'll tell you what, let's rearrange this equation a little bit and say, what if we do this where we basically go through and divide by 57, or like say divide by 24 and multiply by 57 to get this factor on the other side. So basically say that 57 over 24 times T23 is going to be equal to 700 Newton meters. Okay? This is still the sink, and this is now the source. Right? The T23 is still the source, and 700 newtons is still the sink. Is it now possible to make it look just like this? Yeah, what do I have to do? Multiply this by, on this side over here, we're going to have to multiply it by 0.95. That makes sense? That puts it in the exact same form that I had it up there where I had the source and the sink, right? There's other ways I could have done that as well, but anyway. Once we've got it in this form, I probably want to boil it back out again and say T23 is actually going to be equal to 700 Newton meters, right, times 24 over 57, but I'm not multiplying, I'm dividing by 0.95. That's the reason I went through all that in a little bit more of a hassle, like in a little bit more of a formal way, or a little bit more extra work to show it. Why I'm dividing by 0.95, not multiplying. Yes? He wants to know if you can multiply by 0.05. I don't think I would do that unless you actually figured out why that would be okay. So no, I don't think I would try to approach it that way. All right. So once we plug all this in, and in the interest of time, I'm sure everyone can punch that in your calculator. Here's how it comes out. This ends up giving us 310.25 Newton meters. Okay. How do I change that? Because one of the other things we're supposed to find here, right, is both in Newton meters and in foot pounds. So how do I change this to foot pounds if that's what I'm interested in doing? Anyone know those conversions off the top of their heads? Okay, yeah, good. Okay. 4.448, right? That's going to be newtons in a pound. But what else do I need to multiply by here? Okay, one of the things we know is there's 2.54 centimeters in an inch. We might be able to use that somehow, right? So we're probably trying to get rid of these meters. So let's do like 2.54. Does that help me to put those in the denominator? Centimeters per inch. Okay. Does that do it for me yet? Okay, so I got to deal with the centimeters and meters. So, you know, probably what I want to do there is 100 centimeters in a meter. Right? What else? Inches to feet. Okay, so maybe I'll go with the inches up here in the numerator. I'm trying to turn that into feet. So, you know, it's a foot in 12 inches. Am I there yet? No newtons, no meters, no centimeters, right? I'm left with, oh, no inches. I'm left with foot-pounds, right? What I just did right there is the reason many of you are getting some of your questions wrong in homework and on tests. You are not doing this step right here. So I'm just going to give you some encouragement there. It's okay to go ahead and write all this out and do it formally. All right? So once I do all of this, and if I was to punch it in, this ends up giving me 228.83. That's in foot-pounds. Okay? Good with that? What should we do next? Part C. It's a great place to go next. Part C wants to know what's the torque that the motor must supply. Well, what do we have to do? Same thing again, right? Right, we took this, we now have this 310.25 Newton meters. Okay, so T motor is going to be equal to the 310.25 Newton meters, okay, times what ratio? Bigger gear, more torque, smaller gear, faster, right? Smaller gear, less torque, bigger gear, slower, right? So we need to multiply this to find the torque in the motor by whatever direction the ratio needs to be to make that number smaller. Okay? Does that do it for us? Right, we have to, again, just like we did in the last one, right? Just like we did down here, we have to deal with efficiency again because we just dealt with another gear mesh between 1 and 2, right? So that ends up being another place where we have to apply a 0.95 factor down there to account for that efficiency. Okay? And so then we can just plug those in and figure out what that would be. So T motor ends up being 98.49. Okay? Newton meters. Ooh, yeah, we're going to get to that. His question was, what about the motor being 70% efficient? That's the motor's efficiency at turning electricity into torque, turning electricity into the power that's coming out of the shaft, basically, right? And so we will need to deal with that, but we're not quite there yet because what we've done now is just figured out how much torque needs to come out of the shaft, right? And here it is. What is this going to be in foot-pounds? Okay. I'll leave that as an exercise for you to figure out. I'll just report to you that it winds up being 72.64 foot-pounds. Okay? But it's the same factors that I just did down here in this problem. You take those same factors and you multiply them by that, and you'll get 72.64 foot-pounds. All right? Good enough? What about part D? The power the motor must supply to gear 1. Okay? Well, how do we do that? The good news is we just came up with a formula to do that in this lecture, right? P is equal to T omega. Now here's a great spot for me to mention this. You always, if you're using this formula of P equal T omega, you're finding the power for a particular torque applied to a particular piece that has a particular omega. So don't take an omega from one part of the system and multiply it by a torque from another part of the system and say, well, there's my power, right? That doesn't make sense. It has to be the omega at the location where the torque is being applied, right? So, you know, for us, what do? We don't just take 250 RPM and plug it in here because we're trying to do this for the motor, right? So what we need to do is we're going to need to find the P of the motor. We're going to find the omega of the motor and the T of the motor. We just found the T of the motor, right? 98.49 Newton meters. Okay. That we can leave alone. What do we do with the omega? Did we do that down here somewhere? Okay. I've got two expressions of omega motor. One of them's in RPM and one of them's in radians per second. Okay. I recommend using the one in radians per second because you might remember that our T or P equal T omega equation requires that your omega be in units of radians per time, right? So radians per second is definitely in that type of unit of radians per time. And I should have looked at it more carefully. 206.17 radians per second. Okay. So now when I plug that in, right, let's look at the units first before I start doing any of the numbers, right? What happens with radians? Is radians really even a unit? It's tricky because it kind of isn't, right? We know of it as a unit, kind of, but it's just length over length, so it goes away as a unit, right? So we have Newton meter per second. What's that? Okay. Watts, right? It's not, Newton meters would be joules. Then we have that per second, so that would be in watts. Okay. And when we plug this in, it ends up being, you know, I'm actually going to convert this over to kilowatts here, right? So it'll be 20.306 kilowatts. Okay. Now, more fun one. Let's do this in US units. Okay. What is this P of the motor in US units? All right. Well, if we know it's 72.64 foot-pounds as the torque, the speed you can still do in radians per second. You don't have to do anything different with the speed for US units. So 206.17 radians per second. Okay. Now this gives you a number of foot-pounds per second, which is fine. That is a statement of power. But what did it ask us to put it in? Foot-pounds per second and horsepower. So actually, let me go ahead and calculate this. I'll go ahead and tell you what this wound up being. Actually, I don't have that one already done, so we'll have to punch it in. 72.64 times 206.17. Okay, 14,976.8 or 1819 foot-pounds per second. Okay, so that's one of the things it asks us to do, but what else? Okay, it wants us to put that in horsepower as well. Right here it says put that also in horsepower. Okay, so to do that, we take all of this and we multiply it by what? You probably don't remember, but way up here, a horsepower is 550 foot-pounds per second. So when we go down here, we can apply that factor like this. Okay? I need to get rid of my foot-pounds per second, so I put that in the denominator, 550 foot-pounds per second in 1 horsepower. Right? And that ends up giving me 27.23 horsepower. Okay? And if we want, we can actually sort of check this, right? 27.23. What if I take that and look at our other conversion we looked at a second ago, right? The going from watts to horsepower, 745.7 watts per horsepower. Okay. How do I check to make sure that these two answers right here are at least close to consistent? Yeah, take my horsepower and multiply it by, okay, I'll say 27.23, multiply that by 745.7, okay, and that'll come out in watts, right? But it looks like it's about the same, pretty close at least, to the number of watts or kilowatts that I had over here, right? All right, so we did that part. Now, part E. That's what we had some folks in here that wanted to get to, is part E. What do we need to do to determine how much current has to be supplied to the motor? Okay. And I'll just go ahead and let you know, this is a little bit of an oversimplification of how this works, but it's good enough to get the point across, right? There's going to be an efficiency value for this motor in order to be able to supply this energy. Okay, so what is our statement of electrical power for part E right here? What's our formula for electrical power? P equal VI or IV, right? Okay. Now what do we know in that expression? Okay. This is how much power is being delivered to the motor. Right? So I'm going to say this is the power in to the motor. Okay? How much power does the motor produce? Right here, right? 20.306 kilowatts. Okay? Now, how do I apply efficiency? Okay, first of all, what was the efficiency? It says 70% efficient for this motor up here, right? So let's go ahead and say 70% is going to be equal to the useful power out kilowatts, not kilonewtons, divided by the required power in. What else do we know about the motor that might be helpful here? It has 400 volt supply, right? So 400 volts times current, right? So we can just go ahead and leave that in as a variable if you want. Okay. Keep in mind that's a kilowatt, so you know that's, you just have to be careful with that. That's actually 20,306 watts. All right. But when you plug this in, you'll end up getting an I value that is going to be 72.52 amps. Okay. Now, what would it have been if we didn't have to deal with the 70% efficiency of that motor? What if that motor somehow was 100% efficient? Yeah. He says it would be about 50 amps or so, right, if it was 100% efficient. So that efficiency really gets you, right, because the amps is basically what, you know, that's kind of what changes as you supply more or less energy to a real electrical device, is it's your current either increases or decreases. Because usually, at least for most electrical supply kind of things, they very often will receive a constant voltage. Okay? Now I want to show you one last thing that's not even in the list of things that I wanted you to look at. Okay? Someone do this little calculation for me real quick. Someone type in their calculator whatever the this supply power is going to be, right? This we can find that by just taking the voltage times the current. So 400 volts times 72.52 amps. Okay? That's how much electrical power we are supplying. Now, let me have you multiply that by the efficiency of the motor, and then each of the efficiencies of the two gear interfaces where they lose basically 5% each one. They're 95% efficient for each one of those. So let's multiply this by 0.95 squared. Okay? And tell me what you get.
18,325.804.
Okay? And what would the units be on that? 18,325.8 watts. Okay? So that's one interesting value. What we're doing there is we're saying, what would happen if we just applied those efficiencies directly on there? What do you think it might be equal to? Type this in. 700 Newton meters times, and let me go ahead and grab the angular speed I got here a second ago for the machine. Oh no, it was given. Anyway, we'll have to do a conversion. 700 Newton meters times the 250 RPM times what? 2 pi radians per revolution times a minute per 60 seconds. Yeah, we may have had some round off here or there to make them a little bit different. But you see there that what you're doing with those efficiencies, right? What you're doing with those efficiencies is sort of tracing about how much energy survives through each one of those transitions from one form to another, right? And so you can just multiply all those efficiencies together sometimes if they are in series, like these are. You can just multiply all of them together and you can figure out kind of how much overall loss that there's going to be. right? So that's kind of what I wanted to demonstrate there. All right. Any last minute questions?
Can you kind of explain the setup for that equation in number 3? I mean, part E.
Part E? You want to know how to set up the equation in part E?
Yeah, so how do you plug in P out into your VI?
Okay, so what I was doing there was I was plugging in here useful energy out, right, divided by my required energy in, right? And so in the numerator, the useful energy that I'm getting out of the motor comes in the form of the power at the motor shaft, right? And I calculated that down here in part D, right? This was the amount of power that we're delivering from the motor shaft, okay? So that's my useful energy out of the motor, right? The required energy into the motor is just this statement of electrical energy of V times I. I happen to know from the givens in the problem that the motor is being supplied 400 volts DC, right? So V was known, and the only thing I didn't know was my current, right? So plug all that in, and you can solve for your current.
Okay, and you decided to go to efficiency?
Yes, so this is the definition of efficiency. It's useful energy out divided by required energy in, right? So that's all I was doing there, is put all those in there and set it equal to that efficiency value that it says we have for our motor. All right. Good question. Other questions? Yeah.
How come in the description of the question it says the power is with 95% efficiency, but we put that efficiency for the torque as well?
So his question was, in the problem statement it says it transmits the power with 95% efficiency, but when we applied that, we did it for the torque, right? That goes back to what I was explaining in this little segment right here. When you have gears that mesh with each other, if they actually do have gear teeth and those gear teeth are mating with one another and everything, where the energy has to get lost is in a loss of torque, not in a loss of speed, right? Because when you have gears that mate with each other, they can't slip relative to each other without the gears actually, like, you know, skipping teeth, right? And that is not unheard of. It can happen. But your machine is not going to survive, right? Typically, if you start jumping teeth on a device like that, it's a pretty good sign that your machine, whatever you have set up to do this thing, is not going to live very long, right? If that starts to happen. So we generally assume that that basically as speed gets transmitted from one gear to another, it does that part losslessly, which means that the only place that loss happens is in a loss of torque. I don't know if that helps explain it or not, but that's what I was trying to get at with this little discussion that I put up here. All right? Any last minute questions? All right, let's call it good.